So the way we solve this problem is with DP. This is the problem setup. S is the start vertex, T is the end vertex. Now, since we need to find the number of paths with distance less than equal to the optimum distance plus 1, there's only a gap of 1 that is allowed. Uh, this kind of hints for DP. And the way we formulate the states of the DP is, first of all, we'll calculate the distance of all the nodes in the graph via a BFS, or Dijkstra BFS would do, uh, with S as the start vertex. Once we have populated the distance array, we define DP as DP of I0 is number of paths from S to I with length is equal to distance of I plus 0, and DP of I1 is equal to number of paths from S to I with length is equal to distance I plus 1, and the final answer would be DP of T0 plus DP of T1. Right. This is the number of paths with distance with length exactly equal to distance. This is the number of paths with length of paths equal to distance, minimum distance plus 1. Now, an observation here is, since distance stores the minimum distance, let's say that we are currently at node, and from node v is its neighbor. V is the neighbor of node. From the fact that distance is the minimum distance, we can say that node distance of v should be less than or equal to distance of node plus 1. Why this is the case is, let's say distance of v was distance of node plus 2, right? If distance of v was distance of node plus 2, we could have, rather than choosing the path for which distance of v was distance of node plus 2, we could have first come to node with distance of node, then come to v. So the distance of v could have been distance of node plus 1. So distance of v, the value of distance of v has to be less than or equal to distance of node plus 1, and similarly distance of node has to be less than or equal to distance of v plus 1. So we get this inequality. This will help us to formulate the transition of the DP. Now, DP of node comma 0 is 0 if distance of node is equal to distance of v, because then from v, if we go to, from node, if we go to v, we'll have to take one step extra, which is not allowed since we are dealing with 0. And if distance of node is equal to distance of v plus 1, we first of all optimally reach v and then take one step extra to reach node. Um, and that will give us the number of paths as the number of paths to reach DP of to reach node with distance of node number of moves, number of distance of node path length is equal to the number of paths to reach v with distance of v number of path length. And similarly, this is 0 because if distance of v is distance of node plus 1, there's no way we can reach from node to we can reach from v to node with less than or equal to distance of node plus 2 number of moves, which is not allowed. All right, and when this is 1, if distance of v is equal to distance of node plus 1, there's no way to reach to node from v in less than or equal to distance of v plus 2 moves, which is not allowed. No less than distance of node plus 2 moves, which is not allowed. If distance of node is equal to distance of v plus 1, if distance of node is equal to distance of v plus 1, then we'll first of all reach v um, with one step extra and then directly go to node. So uh, that way we have taken distance of v the distance of node, sorry, distance of v plus 1 plus 1. And since distance of node was distance of v plus 1, so we've taken distance of node plus 1 number of moves, which is what we wanted here. And if distance of node was distance is equal to distance of v, we we reach v optimally, and then take one extra move to reach to node. So this is it. This is the transition. The code is straightforward only. First do a BFS to calculate the distance. We're storing D here to calculate D array. Then answer is this, where rec is this function. Yeah.